Thank you very much. I'm an agronomist, so I like to get to the root of the matter. That or I have a real astounding fascination for ramen noodles. I don't know what, maybe 10 years of graduate school or 10 years of schooling will do that to you perhaps. Before we start talking about regenerative agriculture, perhaps it's best to start with what is degenerative agriculture, and unfortunately we have quite a legacy to deal with there. In Georgia, along with much of the Southeast, a lot of damage was done to our soils over the past several years. When the white man showed up to start farming this land roughly had the equivalent of about 4.5% soil organic matter percent. So it was a fairly healthy amount of soil carbon. But by the time we've raked a plow through it a few times and had massive soil erosion events, growing cotton on 44-inch row spacing because that's the width of a mule's rear end, and so that whenever we did get a rainfall, that it was a fairly intense rainfall, oftentimes much of our soil has washed off. You're talking earlier about sediment in some of the streams. We know where that came from. A better part of our soil is in the Atlantic Ocean or the Gulf of Mexico, unfortunately. If you look nationally, we can kind of see that trend here across the Southeast, particularly through the Piedmont here. We've really desecrated the soil. But one thing that kind of sticks out there in terms of soil organic matter is the breadbasket of the U.S., the Plains states in the upper Midwest. Why is it that they have such high organic matter levels? As it turns out, if you look to the grasslands where the major grassland areas were, that's where the soil organic matter is generally the highest. In fact, if you look at where the tallgrass prairie maps lay out, and I'll lay that over top of that soil organic matter map, there's a fairly strong relationship between the two of those. So if we really think about how are we going to regenerate our soil in some way and get to more of a regenerative agriculture, one of the things that we really need to think about is how do we integrate more grassland into that system? One of the things that I do in my job is to try to educate producers on how to better manage their grass resource. Because if we look at what happens when a grass is cut, either for hay or for silage or for grazing, and that regrowth begins, interestingly, the roots actually die back just a little bit, particularly the fine roots, the small roots that are exploring that soil and pulling out nutrients and water. Now, if that plant is grazed again before it has a chance to really redevelop a root system and top growth, those roots will die back even more. And so in a severe drought like what we've had this past year, there's a temptation to keep grazing it until they have nothing but a nub there. And unfortunately, that really does damage to the stand, and that causes soil erosion and other kinds of things as well there too. So what I try to promote is this idea of regenerating the top growth as well as the root growth. Because if we give it adequate rest, it will redevelop. If we give it adequate rest, just like the grasslands were given, as the bison would move south and move back north, grazing as they went, but giving it long rest periods in between, we redevelop the root system there to allow it to have a better cycle there of top growth and root redevelopment. What's really interesting as we do look at the root of the matter is to see the fascinating interactions there between the root and the microbes of the soil, and particularly the fungi that are active in collaboration with the root. Here we have a prominent taproot, okay, a prominent taproot here and the root cap here, and the root cap is where it's protecting that root as it's expanding into the soil. And we have these little fine roots that are doing the same sort of thing. They have their own little root cap. And then we have fungal mycelia that are acting in association with that root. In fact, those fungi will actually grow around an individual cell, and that cell will provide that fungi a little bit of sugar, and that fungi will go do some work for it. It will go looking for water and nutrients. It will actually chemically extract some nutrients out of the soil and to provide that to the root and to the plant. So there's a lot of work that's going on there. Now, of course, as I mentioned earlier, when we graze, those fine roots oftentimes will slough off. They'll die back. They'll reestablish again, but there's a time there where they have gone away. And so that's adding carbon and some substrate there for the other microbes of the soil to act upon. If we look at this in terms of soil structure as well, it's exuding a lot of sugars and proteins, and in particular glomalin, which is actually a glue that kind of binds the soil together. It really helps to protect aggregates in the soil. And it also allows for better aeration of the soil and more water infiltration into the soil. So if we look at this under a scanning electron microscope, here is a root hair in this particular case, and all of these little fungal mycelia are coming off of that root and actually penetrating down deep right in between the plates of a soil particle. And what's really interesting is that when this goes away, if this sloughs off, this one has actually been sloughed off because of how it was put onto the scope. But you can see what will happen is that a little bit of this is trapped and collapsed underneath that soil. It's protected from any change until we put a plow through it, until we do some sort of mechanical disruption there. In fact, a long-term trial that was done in China, in some of the grasslands in China, they were looking at soil organic matter development. In case you're not aware, soil carbon and soil organic matter you are interchangeably, basically, for all intents and purposes. But as root production increased, so did soil carbon increase. As root turnover increased, so did the rate of soil carbon increase. So it's a fascinating example of how this is occurring over a long term. But how quickly can this occur? Well, there's some interesting things going on in Georgia at the moment with regard to our pasture-based dairies. We're blessed with a climate that allows us to graze throughout the majority of the year. And so as a result, some of our dairies have transitioned over to a rotational grazing system, giving their pastures rest, but they're out on pasture for the majority of the year. In fact, here is Andrew Peachy, one of our dairymen who's made that conversion, a guy who's very passionate about his farm, his family, his cows. And many of the dairymen that I work with are in that same sort of scenario. And a very scenic scene there behind him. And what's happening here, over the past 25 years or so, we have seen the number of dairy cows in the state of Georgia drop like a stone. We have really seen a large decline in the dairy industry in terms of dairy numbers. Now, if you actually look at milk production, it's actually fairly stable. It hasn't decreased at nearly that same rate. But then all of a sudden here in about 2006, 2007, which incidentally, and I do say incidentally, is when I came to Georgia. I didn't have much to do with that. I contributed, but not much. But we started seeing an uptick there. What was going on? Well, as it turns out, we see a huge number of pasture-based dairies cropping up. And the number of dairy cows on pasture-based dairies in the state of Georgia now represents about 20% of the overall dairy herd. So we were curious as to what was going on these farms, because many of these farms were going into cotton and peanut fields that had been tilled over and over repeatedly for probably the last 30 or 50 years. So we were taking some initial soil samples, and a colleague of mine started taking some of these soil samples in 3 different paddocks. These are subdivisions of a pasture, okay, so they may have 50 individual paddocks on a farm. This is 3 of those. So P4 is paddock number 4, P8, and P14. The average soil organic matter was just over 1%. Fairly typical of our soils now, unfortunately. But over time, he tracked those each year, and at the end of 3 years after the conversion, they were at 2%. And he brought that into my office and shared with me that number, and I said, "You are crazy. No way. That is not possible." Because of the amount of biomass that is required to do that, I just didn't think it was possible. He said, "Well, okay, I'm going to prove you wrong. Do you want to be on the grant or not?" "Sure, I'll be on the grant with you, because I want to make sure you're doing it right. So we're going to do this." So we went back and we looked at this in what's called a chrono sequence. And I want to really give proper recognition to Dr. Aaron Thompson, who is the lead author on this. And then he had a great postdoc student here, Megan Mockmuller, who did a great workup of this data. And we looked at a chrono sequence of these as we looked at over time the buildup of soil carbon here. And sure enough, we were getting that same 1/3 of a percentage point increase in soil organic matter over that time. In fact, it keeps increasing until about year 10, then begins to plateau out. And interestingly, about 4.5% to 5% organic matter, which is kind of the native soil levels. So let's think about how much of an impact this can really make. We're academics after all, so we can do some mathematical exercises, right? What kind of impact could this make? Well, across the Southeast, there are approximately 9 million hectares or 22.2 million acres of degraded, low organic matter row crop ground in the Southeast. What if we just took 10% of that land and converted it to these pasture-based dairy systems? Not even dairy, by the way. This could also happen in beef cattle enterprises as well. But in that, we would accumulate 4.5 teragrams of carbon per year. Actually, I had to look up what a teragram was. I didn't know that many zeros could go on the end of a decimal point there. For perspective, I think it's always easier to think about this in real world terms. That would replace the annual emissions of 3.5 billion cars. 38.4 billion barrels of oil, 4,332 coal-fired power plants. I didn't do the wood pellet conversion, but pretty close. We're talking a huge number, and considering that there's only 1,300 at the end of 2012, there were only 1,300 coal-fired plants in the U.S., and we're the biggest one in terms of the numbers. It's a huge amount. So I'll leave you with this ethic that many of our producers work with, and it was an ethic that was taught to me from the very early age of growing up on the farm. If you take care of the land will take care of you. My contact information is all available on our website there. More information about what we're doing with this project and many others is available there at georgiaforages.com. And thank you.